Okay, cool. Okay, well, thanks very much for coming. Hopefully I'll try and make the material as accessible as possible. A lot of people find parallel programming and their paradigms quite scary, but hopefully by the end of this talk you'll realise that the concepts are quite simple, and certainly the execution of parallel programming can be subordinated quite easily as well. And today, well, my name's Richard Paul. I work for a company called Bain Core, and we're a partner of Intel, and we specialise in the parallelization of code, using a lot of the tools that Intel have available on the marketplace, and their compilation tools and their analysis tools, and also some tricks and techniques and third-party tools that we at Bain Core have become familiar with over the years. Today I'm going to talk to you about a paradigm called Intel CILK Plus, which has been around for quite a while. It was first developed by some boffins at MIT about 20 years ago, and it has some advantages over some of the other parallel processing kind of paradigms, really. So what is CILK Plus? Well, it's a kind of an extension for C and C++ languages that allows for kind of for easy data and task parallelization. It's an open specification, and it's portable across kind of multiple operating systems and processors. It's officially supported by Intel and the GCC compilers. And the philosophy behind Intel CILK Plus is that the programmer concentrates on exposing parallelism and exploiting locality of data variables, and that the runtime system is therefore responsible for scheduling and efficient execution. And it hinges upon three simple keywords, really. So you've got CILK underscore spawn, CILK underscore sync, and CILK underscore for. So when we talk about spawning a process, do come in, yeah? Problems? Toast, 1, 2, 3, 4, 1, 2, test, 1, 2, 3. Hi there. Please come in. Yes, I've got the signal. Is everything okay? Shall I continue with my talk? Yeah. Hi there. I'll just recap. The philosophy behind CILK Plus is that the programmer concentrates on exposing parallelism in the code, and also trying to drive the compiler to exploit locally defined variables or locality. And the runtime system is then responsible for scheduling and efficient execution of that application. And we do that effectively by controlling when threads begin and end, and when they're created. And the three basic keywords for CILK Plus are CILK underscore spawn, which allow you to create a kind of a new thread, CILK underscore sync, which is effectively a barrier operation, which mandate the compiler to pause, or the program counter to pause until all of the threads have terminated at a particular point in the program. And obviously anyone who's had any prior experience of parallelization will know that when you have for statements, those are kind of prime candidates for parallelization. What you do is you unroll your for loop, and instead of having one thread execute each iteration of the for loop, you have multiple threads basically executing individual iterations of the for loop, and that way you can parallelize. So that's what the CILK underscore for keyword is there for. Reliability of the calculation that are done using CILK Plus is ensured using reducers, and we'll talk about that a little bit later in the talk. And array notation and SIMD functions are also supported. You may have You may be aware of those if you've been exposed to kind of OpenMP or MPI. And there's also an API which enable you to control values of various environment variables, which control the maximum number of threads and timeout mechanisms and so on. Okay, so why use CILK Plus parallelism versus MPI and OpenMP? What are the virtues of CILK Plus over other constructs such as MPI? Well, Intel CILK Plus can work over shared memory machines. That's its main virtue. And it has more features than MPI. And I've kind of enumerated them there. But, to cut a long story short, there are a number of features that CILK Plus supports over and above MPI, and also it can work over shared memory machines. And I've also put together another slide here, which is comparing CILK Plus with some of the other parallelization techniques, such as OpenMP and thread building blocks as well. So OpenMP is largely regarded as a de facto standard for shared memory programming, and it provides an API for the fork join model, and threads communicate by sharing variables. And OpenMP has been historically used for loop-level regular parallelism through compiler directives. And thread building blocks, it's another parallelization scheme that Intel make available. And it's based upon object-oriented C++ runtime library that contains data structures and algorithms to be used in parallel programs. It abstracts the low-level thread interface. However, conversion of legacy code to thread building blocks requires restructuring certain parts of the program to thread building block templates, and that kind of constitutes kind of an overhead in software engineering terms. So in comparison, Intel CILK Plus it's easier to use, and you get kind of more direct and quicker results because it relies upon those three very, very simple keywords. And a lot of the complexity of managing the parallel threads is really devolved to the runtime system. All you need to do is be skillful about where you put those three keywords, CILK spawn, CILK for, and CILK sync. And really you can rely upon the compiler and the runtime system to do the scheduling of the threads for you. And we'll talk a little bit about how that scheduling actually works a little bit later on in the talk, because it's kind of quite sophisticated. Okay, so what do you need in order to use CILK Plus? Well, the good news is it's supported by a number of different operating systems: Microsoft Windows XP or later, Linux. In addition, you need to have the Intel C++ compiler installed with one of the following product suites, either Parallel Composer or C++ Composer. That's not too much of an overhead in terms of kind of underlying software. And once you've got that kind of software environment available, then the facilities of CILK Plus are available to you as a developer. Okay, so the next slide is really encouraging you guys to think about how you kind of analyze parallel programs, really. How many of you come from a kind of a formal computer science background? Hands up. How many of you have actually done a formal computer science degree? Right, okay. So those that have done a kind of a formal computer science degree may be familiar with the concept of a graph in mathematical terms. And a graph is really just a set of points. If you imagine a set of points sprinkled on a piece of paper, and they're connected by a set of edges. So you have a set of points or vertices connected by a set of edges. And if those connections are directional, so a connection between from A to B is not the same as the connection from B to A, yeah? If there's directionality in those vertices, then what you have is a dependency graph, a directed dependency graph. And you can use the mathematical concept of a dependency graph to really specify how the threads permeate through your application program, and figure out where the main computation is happening and where the synchronizations are happening, and where and why the computation is being stalled for various reasons. And once you've got an idea of how the computation in your application is proceeding through your dependency graph, you can use a number of different metrics to specify the time it's taking for that computation to proceed. So T1 we can define as basically being the overall work needed to complete the overall task. That's assuming we just do the task in serial and there's absolutely no parallelization whatsoever. TP is the execution time on a single processor, given that we're now in a parallelization regime, and T infinite is the work needed if distributed over a large number of processes. But we know that if we distribute the work over a large number of processes, it's not the same as just dividing the work amongst those processes. There are communication and synchronization costs. So the rule is that this inequality, which is the kind of the penultimate bullet point, holds for obvious reasons, right? There's another rule from parallel programming, which is kind of the final bullet point. So that's a little bit of theory, really. But what is parallelism in our programs? In a multiprocessor system, we can define task-level parallelism when each processor executes a different thread on the same data, and the threads may execute the same or different code. In the general case, different execution threads communicate with one another as they work, and communication usually takes place by passing data from one thread to the next part of a workflow. And we also have data parallelism, and that occurs when in a multiprocessor system executing a single set of instructions, data parallelism is achieved when each processor performs the same task on different pieces of distributed data. In some situations, a single execution thread controls the operation on all pieces of data. In others, different threads control operation, but they execute the same code. Yeah, so there are two different kind of flavors of parallelism there. Okay, this slide here is really just a kind of a summary of the CILK Plus language features, and you can see that it's relatively simple. We've got a number of different keywords which we've touched upon: CILK Spawn, CILK Sync, CILK 4 I've talked about. You can refine the properties and the behaviour of the CILK 4 keyword by specifying CILK grain size, which basically specifies the stride within the for loop. So instead of simply saying, right, one thread will execute one iteration of the for loop, and then another thread will execute the subsequent iteration of the for loop, it may very well be that you would want each thread, for instance, to execute kind of three or four iterations of each for loop, and you can control that by using the kind of the CILK grain size keyword. And also, very importantly, there's another keyword which is CILK serialize, which specifies that that particular portion of the program has to be done in serial. And that's very important for obvious reasons, locking mechanisms, for instance, or risk of data races, or kind of, you know, so on. Or obvious reasons why you would wish there to be kind of serial parts of your program. And there are a number of kind of key environment variables. The number of threads can be specified through CILK NW workers. And also you can specify certain properties of the language extensions using Intel underscore extensions. And all you have to do really at the top of your C and C++ programs is specify certain header files to ensure that the compiler knows that you want to include certain functions to support the CILK Plus paradigm, and they're specified at the bottom 4 or 5 rows of that table there. Okay. So hopefully it's not too scary one way or another, but hopefully you can see that there are a number of benefits through enabling your C and C+ programs to be parallelized. There is a skill associated with knowing when to use these particular keywords, but it's a very, very simple paradigm, certainly in comparison to OpenMP and MPI. And as I say, it works on shared memory systems, which is a virtue that MPI doesn't have. And it's been around for a long time, this paradigm. Okay, so the next slide is really just an indication of how you would kind of take a program and basically parallelize it, a kind of a generic meta recipe, if you like, for taking a serial program and turning it into a parallel program. And in general, there are 6 basic steps that you have to go through. Obviously, the devil is in the detail, and it may very well be that you'll come up against various bugs associated with the data structures that you're using and the control flow logic that you're using to do with your application. But in general, you're going to have to do these 6 things. The first thing to do is to debug the serial version of the program. Because parallelizing a buggy serial version of a program is very, very difficult. So you basically need to make sure that your serial version is as free of bugs as possible. And then the next thing you need to do is identify the regions of that program that will benefit from parallelization. So the hallmarks there are kind of long-running regions where you think your program counter is going to spend a lot of time in proportion. So kind of not initializations of variables, for loops or kind of while loops that kind of run and kind of refine the calculations. But the key there is that you need to try and make sure that you have very, very few data dependencies in your for loops and in your while loops, right? And then once you've identified those most responsive regions in your program, you can basically use the keywords CILK spawn, CILK sync, and CILK for. You obviously include the header files, and you configure the environment variables as we've specified in previous slides. And then you build the program using the correct kind of Intel compiler directives. And then you verify the program by checking that the serial version results are the same as the parallel version results. And if this is not the case, then they're likely to have been kind of data race conditions between the variables, which will bring me on to the concept of reducers and holders, which we'll touch upon in a few slides. And we basically correct those race conditions by using reducers or holders or locks, or if needed, we might need to kind of recode some aspects of the program, typically to get rid of some data dependencies, really. Okay. In addition to those 6 steps, there are some things we can do to kind of to tune the environment, I suppose. The first thing is we can kind of overload the environment. The default is that you set the number of threads to be the number of cores on the system. But it may very well be that there are certain kind of holding points in your application. Certain threads get delayed because you're waiting on locks and stuff like that. In which case, it's perfectly fine to overload the system by increasing the number of threads, and that will just give the processes something more to do when they're waiting for other processes to conclude. The next point is really talking about data races, which is something that we've talked about before. The Intel CILK Plus SDK does contain a very, very useful tool, which is a screen race detector, and that will help you basically determine where and when these data races actually occur, and they can often be the kind of the real kind of mire of the parallel program. Okay, so this slide here is really just talking about some details about how and when you use CILK Spawn and CILK 4. There are some subtleties about how you would call those functions, primarily because you want to ensure that there's no hierarchy of threads when, in particular, the CILK Spawn and the CILK 4 keywords are actually caused, because you, like we said earlier in the presentation, the managing of the threads within the CILK Plus paradigm is really devolved to the operating system, and you don't want to interrupt that managing of the threads, really. So there's some subtleties about how you specify functions and how you kind of call those keywords, but I'm not going to dwell on them here. Similarly, there's some subtleties there about how you use CILK 4 grain size. Onto a little bit more kind of theory and conceptualization. So we talked about threads. A strand is a kind of related kind of concept. A strand is a sequence of instructions in a program without any parallel control structures. And a maximal strand is a strand that is not part of a longer strand. And what that enables you to do is to, I suppose, kind of visualize how different parts of your computation are interacting to kind of create the whole application, if you like. And we talked earlier in the presentation about the directed acyclic graph, and this slide here is an example of a directed acyclic graph. And there are ways of kind of using this kind of conceptualization to figure out where the locks and the synchronizations in your parallel program should be. But what you can also do is you can kind of form the strands in terms of a kind of a hierarchy, and that brings us onto another concept, which is the one of pedigrees. And this is a way of kind of specifying the importance of a strand within your entire parallel program, really. And in the Intel CILK Plus paradigm, we basically kind of define a program by a collection of pedigrees, which have a particular way of kind of being specified, a variable length sequence of a 64-bit integer. And a maximal strand boundary occurs at each of the keywords, CILK Spawn, CILK 4, and CILK Sync. And they basically they satisfy a number of properties: uniqueness, lexicographical ordering, and determinism. And I'm not going to go into too much detail about what that is, but that gives you an idea of how the system is able to kind of manage the parallelization of a program, and how this kind of this under the hood parallelization and prioritization of threads is actually managed by the system. Okay. We've said before that work is defined as the total amount of processor time needed to conclude the algorithm. Span is the critical path, the most expensive path from beginning to the end of the program. Parallelism is defined as a speed up achieved in the execution time if the program was to run on an infinite number of processors. And basically what happens when you do a kind of a CILK 4 or a CILK Spawn is that the system acts to kind of to load balance between threads. So it kind of iteratively creates more and more threads. As it detects, it can kind of share the work, the work of the program amongst those threads, and it works to kind of to load balance those threads using a greedy algorithm, basically. So it mandates the threads to seek extra work if they've terminated on a particular subtask. So all of these threads, basically once they're spawned, basically compete for work in the program, and that's a way of kind of dynamically load balancing the work of the program amongst the available threads, and that's in contrast. That's in contrast to how things like OpenMP and MPI work, right? This is a very, very important point. OpenMP and MPI don't have that dynamic load balancing property. What they really rely upon is that the programmer knows what they're doing, and the programmer sets various environment variables to just distribute those threads amongst the available cores. But here in CILK Plus, you can override the CILK Plus mechanism, but it's not recommended to do so. Really, the best way of using CILK Plus is really to let the operating system kind of manage the threads and manage the workload that's placed upon those threads. Okay, so you have your serial program, you've parallelized it using the kind of recipe that I specified earlier in the talk. You've debugged that, and you've made sure that there's consistency of results between your serial version of your program and the parallel version of your program. And you're running your parallel program kind of perfectly happily. And what you basically need to do is to get your results out. So how do you do that? Well, obviously you've got a whole bunch of threads, and each thread holds a kind of a portion of the result that you actually want. You now need to find a way of kind of combining all of those sub-results, if you like, in a kind of computationally coherent way into the overall results. And the way you do that is you have a series of reduction operations. And reduction operations are pervasive in other parallel paradigms, such as OpenMP and MPI and others as well. And this slide kind of specifies a little bit about the properties of reduction operations. But basically what they are ways of kind of combining sub-results that are held by individual threads into an overall result, maintaining the coherency of the calculation, and they don't require things like locks or mutual exclusion processes or mechanisms and so on. In mathematical terms, a reducer is actually what's known as a monad, if anyone comes from a kind of a mathematical background. But basically what that means is they're associative, and also you can kind of string them together as well in various kind of useful ways. And CILK Plus, the CILK Plus environment provides us with a number of kind of standard reduction operations. They're things like the maximal reduction operation, or you can OR the results together, or you can AND them. You can take the minimum values, you can add them, you can exclusive OR them. And like I say, all of these different kind of reducers can be strung together to create kind of more complex computational procedure for combining the operations. And they're inherent in the CILK Plus environment. The other kind of computational aspect that I'd like to introduce you to is the one of holders. So that's really the operating system forming a kind of a series of data structures by which it can kind of hold these kind of partial results that each thread has during the execution of the process. And again, there are ways of kind of manipulating the holders, but largely that complexity is managed for you by the CILK Plus environment. So the CILK Plus environment is actually doing an awful lot for you, and between the functionality and facility of reducers and holders, the CILK Plus environment is really ensuring that the parallel calculation maintains its coherency. Okay, and that's pretty much it about CILK Plus. So hopefully in half an hour I've given you a flavour of a very, very powerful and hopefully easy to use paradigm. Thank you very much indeed. Thank you.